Hi, today we're going to be learning about how to calculate something called a difference quotient. And we're going to be looking at it from a couple of different perspectives. There's some vocabulary in here that you're going to become familiar with, and also some pictures that we're going to take a look at. But in essence, all we're doing is calculating a derivative. And we're doing that by using the same slope formula that we've used all the way through. So let's start by talking about what a difference quotient is in a pretty straightforward kind of a way. So if, for example, I'm talking about a difference quotient, what does that really look like? Well, it really looks like the same definition of a derivative that we've seen before. So we're going to take f of x minus some f of c, and sometimes we're going to have c be the point of interest. Sometimes that's going to move around a little bit, but that's what we're going to talk about with the difference quotient, over x minus c. This basic format is going to be used in the difference quotient, and all we're going to do is plug in numbers in slightly different ways. So let's talk about the three types of difference quotients that you can make. The first one is called a forward difference quotient. And what I'm going to do at this point is bring in a picture, and that's going to tell us a visual display of what's going on with the forward difference quotient. Okay, so here's a picture of a forward difference quotient. Notice that the value x that I'm interested in is actually here, and the f of x value that corresponds to it is here. And what we're doing is we're saying, let's look at, in order to calculate our difference quotient, let's look at a distance that's just slightly to the right of x. So we're taking x plus some h. This h, by the way, we're going to call the tolerance for this particular difference quotient. And we can make h large, we can make it small. Generally, it could be a small decimal value like 0.01 or 0.1. Notice that x plus h also corresponds to f of x plus h that we would get simply by plugging the value into the function itself. And what we're going to do to calculate the difference quotient is we're going to take the delta y, which is shown here in the picture, right in this spot. That's going to be achieved by taking f of x plus h minus f of x and dividing that by x plus h minus x. Now if you think about it for just a minute, in the bottom of this fraction, notice the two x's are going to cancel, so really what we're going to be left with there is just plain h, which is shown down in here. Okay, we have delta y divided by h. That's what a forward difference quotient is going to look like. Let's take a look at the next one, which is called a backward difference quotient, and see what's different about that. Okay, so here we have a backward difference quotient. Notice we still have the same x, we have the same f of x, only this time we're taking a value slightly to the left, so we're subtracting the h value tolerance instead of adding it, and that produces an f of x minus h. We're still taking delta y and dividing it by what will essentially be h, because we're going to take x minus x minus h, and that's going to, basically the x's are still going to cancel out, and we're going to be left with just the tolerance h. So that's going to look very similar. The last type, there's one more type, and it's called a symmetric difference quotient, so we'll take a look at what that is going to look like. Okay, notice in the symmetric difference quotient picture, here we have x, and here we have f of x, only this time we're actually going to choose values on both sides. We're going to choose x plus h and x minus h, and then that's going to produce an f of x plus h and an f of x minus h. And what we're going to do to use the symmetric difference quotient is we're actually going to take these two values on either side of f of x and subtract them. That's going to make our delta y. Then we're going to take these two values and subtract them. That's actually going to give us h on one side and h on the other side, or 2h. So how do these look with actual numbers and an actual function f of x? Well, let's take a look and see what we get. Let's take f of x equal to a really simple function, x squared. And let's take another very simple x, say x equals 3. And we would like to estimate the value of the derivative using both a forward, a backward, and a symmetric difference quotient. So let's do the forward difference quotient first. So we're going to take the difference from x equals 3 with a tolerance of, say, 0.01. What we're going to do is calculate part of the difference quotient using these values. Okay, so to make this calculation, here's what it's going to look like. We're going to take the function value at 3.01, slightly to the right of 3, minus whatever we get when we take f of 3. We're going to divide it by 3.01 minus 3. So those are the numbers that we're going to need. The bottom part is easy. When I take 3.01 minus 3, I'm just going to get 0.01. The other part I actually have to do a little bit of work on. I need to square those numbers. So I get 9.0601. I do want to keep this number without round off, and that's going to be minus 9. So I'm going to do that calculation without any round off or any type of change here, and I'm going to get 6.01 as my value for my forward difference quotient in this particular case. Okay? Remember that this is just an approximation for the value of the derivative at x equals 3. Eventually we're going to do something much more precise, but for now, just approximation. Let's take a look at what a backward difference quotient would look like for this very same thing. All I'm going to do here is just erase. I'll leave the function and the value. Okay. And we're just going to take a look at what happens when we look at it as a backward difference quotient. I should have left my h too. So I'll put h back. So how does this change with a backward difference quotient? Well, now we're taking a value slightly to the left of 3. So since h is 0.01, we're going to be taking the function value at 2.99 minus the function value at 3. And then on the bottom, we're going to take 2.99 minus 3. You might say, well, could I switch those? Could I take f of 3 minus f of 2.99 and 3 minus 2.99? And the answer is sure. I'm just doing it this way to show you that if you choose an order, the key thing is that you keep things in the correct order. Notice that in the bottom, my difference is still just h. It turns out that it's negative, but so will the numerator. That value is also going to be negative because it's going to be 8.9401 minus 9, which is also going to be a negative number. When I do that subtraction and divide by 0.01, what I'm going to get is about 5.99, and the negatives are going to cancel each other out. Notice that when we did the forward-backward difference quotient, we got a number just a little bigger than 6. The backward difference quotient, we got a number just a little smaller than 6. Let's see what the symmetric difference quotient would give us in this case. And of course, we're expecting something right around 6, pretty close to it. Okay, so here comes the symmetric difference quotient. So now we're going to take the value that's a little to the right minus the value a little to the left. So we'll take 3.01, f of that, whatever the function value is for that, minus f of 2.99. So we're on, equal distant on either side of the value that we're interested in, which is 3. And then 3.01 minus 2.99. Notice that the denominator is now larger. It's 0.02. It's 2 times h. The numbers in the numerator are going to be the ones we've already seen. So for example, we're going to have 9.0601 minus, and then from the previous question that we did, 8.9401. Sorry, I ran out of room there. So when I subtract those two, I'm going to end up with 0.12 over 0.02, and you might be able to see where this is headed, because when I divide those two, I get exactly 6. So not terribly surprising. that my symmetric difference quotient is probably going to be somewhere in between my forward difference quotient and my backward difference quotient, all three of which are good approximations for the value of the derivative for x squared at x equals 3.